Okay, before we start, a few remarks, important things before we start angular momentum for a system of particles today. So I sent you an email, I put it on Canvas, I put it all over the place. I'm sorry I have to change my office hours to 1 to 2:30 p.m. Same days, just 1 hour earlier. Picking up daughter from school makes you do that, sorry. So I hope that doesn't affect too many, and if today you were planning to come after 2:30, send me an email, I guess, because other days I will be able to actually stick around after 2:30, but not today. So, okay. Then, a few remarks that may be useful, actually just a couple of them are useful for your test, but one is about these reaction forces. I've got a couple of questions via email about where still people don't understand exactly how we model them, where we assume they are projected. So, there are two different scenarios. They're actually the same, but may look different, which are the following. Your particle object is moving in contact with a surface. In the most general case, it's an actual surface, S, right? And that's what we have sketched several times. In which case, we assume, remember, for the forces, we are making up models. We are assuming things here. So we decided that for this case, where you're moving on a surface, we call T the tangent plane in P, and the reaction is, the friction force. The friction is on that plane. And then we say, okay, in P, we can always define the normal to the surface, which is the direction normal to the tangent plane, and along this, we would have the reaction. If this collapses to a line, and this is a rigid surface, by the way. Okay, we said that when we introduced contact forces. If that surface is instead a line in 3D Euclidean space, which it's still a rigid surface that collapses to a line, so it's a rigid line. In this case, we say, okay, the friction is along what we call the ET direction. So here you have friction, and the reaction is along the plane, which is perpendicular to ET. So on these two, you will have your reaction. Now remember that when we defined this intrinsic coordinate, we said this depends on the reference frame. So if this curve is actually, it's a rigid curve, so it's a guide. It's your ring for the example that we've seen a few times, whatever that is. So it's a rigid track that it's moving with respect to this inertial frame. Then a point P on the line, on the track, will have a velocity which is probably not in this direction. In general, that may be the case. So for the general definition that we have given of intrinsic coordinate that goes with the point moving in 3D Euclidean space, it really depends on the reference frame where you are. But when it comes down to projecting reaction and friction forces, what you really want to do is basically define ET, EN, and EB as seen by an observer that is a guy sitting on the curve itself. So you're putting yourself in the reference frame, which is attached to that rigid surface in this case, line in this case. So bottom line is you have a rigid surface or a rigid curve in 3D Euclidean space where your point is you want to basically define the tangent and the perpendicular plane in this case, tangent plane, perpendicular direction. There are properties of that particular surface. So if my surface on which I'm moving is this board, this is the tangent plane to itself. It's a plane already. And the normal is this direction. It doesn't matter if I take this board and I move it around. They remain the same. So you still write the reaction of a point that is moving on the board with a component along the normal to this board. It doesn't matter what the board is doing in space. And the friction is on the board. Does it make sense? So they are slightly different things. We defined the intrinsic coordinates in general when we did that one lecture. So they are in general coordinates that go with a particle that it's moving in 3D Euclidean space, and they do depend on who is looking at that motion. This is in general. That was kinematics. That was a definition. We created that coordinate system. When you need to then represent forces, contact forces, right, reaction and friction, then you may still use intrinsic coordinates, basically the definitions we have given. Just be careful that you need to be defining them being an observer fixed to the curve. So basically the curve in this case becomes your A reference frame from which you're looking at things. So you're sitting on the curve and you're looking at this particle moving on the curve. Because friction will be tangent to the line in this case, tangent to the surface in this case, reaction is normal to the line, normal to the surface. That's what you want to do always. It's just an agreement, it's an understanding among people doing dynamics that that's the way we want to write friction and reaction. Remember, these are all models. But if you don't do it that way, you're going to make your life very miserable. And by the way, this leads me to the next comment, which is there are a couple of subsections on your book about this. How you represent contact forces when you have a surface, when you have a line, rigid line in space. I hope you guys are reading the book. My lectures are not enough. You have to go and do your problems. You have to go and read the book, the sections that correspond to these lectures, because that's what I outlined the first day of class, and because you're graduate students. So you really want to go and study the theory a little more than what I just tell you here. I'm not saying that you should study more material and do completely different things that we're not covering, topics that we're not covering, but this is there. Reaction forces we have seen. So if this is not clear, make sure it's clear in your mind that that's the way you do it. Slight difference between a generic intrinsic coordinate that does depend on who is the observer and the intrinsic coordinate that you build because you needed to write these two things. If that's your goal, then your intrinsic coordinates with respect to the curve itself or with respect to the surface itself. So in other words, they are just the geometric tangent and normal to surface, a line, nothing else. Doesn't need to be more complicated than that. And again, if this is my line in 3D Euclidean space, and of course the tangent, it's the line itself. It doesn't matter how it's moving, what it's doing. The tangent is just always the same. It's the property of the line. So does it make sense? I wanted to clarify because some people had some confusion on this. That plus just a few more observations about two problems that we have solved recently. And I do hope that you go back home and you resolve all the examples we see together from scratch by yourself, because that's the way to go, or at least that's my suggestion. So this is what I just wrote down in my quick note here. I think this was the equation of motion, more or less, that you would get for the parabola problem. I just want to make a quick comment. I'm not going to do any more calculation, any more derivation, nothing. But I think if you manipulate what we got last time, regardless of using the work energy theorem in the classical form or the alternate form with the potential energy, I think we were getting something like this. By collecting x dot, it will look like this. In fact, I think we had x dot all over the place. I didn't collect it at the time. So when you have something like this, of course, this is your equation of motion, and we said we only expect one in the variable x. But what would you do here? How would you give me the equation of motion? This is going back to really first year, but people do make these mistakes. And I don't want you to have this on your test. People will do this, right? No? Yes? What would you do? Which one? Would you just give me this as the equation of motion? I mean, it's fine, but it doesn't need to be so ugly. There are two solutions here, right? This is a product. There is a product here. So the equation of motion can either be this, which is a pretty boring solution, but it's fine. It's one. And then the rest. Both of them are solutions to that problem. So you do have two different, if you want, two equations, but really the one that I care about is this. Why? Because this is dynamics. I want stuff moving. This is not moving. Okay. Just wanted to clarify. And then the last comment is about last lecture, I believe, where we left off. We said, okay, body diagrams, when you have systems of particles, you can't just do the individual body diagrams. You also have to combine them to get equations. And I do believe that the combined one, I went back to my notes, and I had something like this for the wedge and the block. This is the system's equation of motion. It will look like this. x1 double dot ex plus m2 m1 plus m2 x2 dot little ex. That's it. Well, we just left it there and we didn't say anything else. Well, obviously here you can see the beauty of this equation that can be combined with one of the other two coming out of the free body diagrams for the single particles, which is if I dot both sides with big Ex, and the dot product is commutative, so I can do it, on the left or the right. This completely goes to 0, and from here you get 0 equals mx1 double dot plus m2 over m1 plus m2 x2 dot, and this dot product, I think it comes down to be like cosine of the beta angle of the wedge, something like that. So that would be your other equation that now you can combine with one of the other two and really get some meaningful result for the equations of motion of the system. Questions, concerns? I just didn't finish this. I didn't do the dot product last time. Okay. Moving on. Everything is good? All right, so as we've done with a single particle, we are going to extend the concept to systems of particles, angular momentum of a system of particles. Remember, these particles are called pi. Each one of them has a mass mi, and their positions with respect to a given origin. Particularly in this case, we'll look at an inertial reference frame I'll call Ri. Okay, it's not going to be that much different from what we've seen for a single particle in the end, but it is very different in the way you use it because you have more than one particle. So let n be an inertial reference frame and Q, exactly as we've done with a single particle, a generic point in E3, 3D Euclidean space. That's all we need. And of course, we have a system of particles. So definition, we call H with respect to Q in N the angular momentum of the system of particles in an inertial reference frame with respect to point Q, the summation over I of Ri minus Rq cross with Mi Vi as seen by an observer fixed in N minus V of Q as seen by an observer fixed in N. So this is that. I don't need to rewrite it here. That's our angular momentum. Of course, is as seen by an observer fixed in N with respect to a generic point Q. And there is really nothing new here. We just didn't have the summation over I last time. Okay. And this that I'm going to derive is an alternative to using the results we have seen last time for certain problems where you may have points that are not inertially fixed and geometry of problems where using the angular momentum to find equations of motion may be convenient. So it is up to you through solving problems, realizing when these that what we're going to derive is going to be more useful or not, and someone may be just asking you solve the problem with angular momentum. So guess what I'm going to do now? Take its rate of change. That's all we do here. d dt in n of is going to take a little bit of steps here because of the summation. Not that much. All right. So at this point, you should really be able to go through this because you have all the tools to do it. So this may actually be a question for a test, but this is a derivation that we need. So I'll do it. But again, there's nothing secret or difficult here. You do have all the ingredients. So that first term, Ri minus Rq, gives me Vi in n minus Vq in n. Remember the derivative, the rate of change is with respect to n, cross with Mi Vi n minus Vq n, and that's the derivative of the first cross the second. Then I have summation over I of the first term, Ri minus Rq, cross with Mi A of the genetic particle I as seen by an observer in n, A of Q as seen by an observer in n. First term is that is 0. Same thing that happened last time with a single particle. So that's 0. Okay. Let's look at this one here for a second. I'll split these two accelerations, and I get summation over I, Ri minus Rq, cross with Mi Ai in n, minus summation over I. Of course, this I is going from 1 to n. I just don't want to write it every time. Ri minus Rq, cross with Mi Aq in n. Okay, tell me what to do. Let's do one piece at a time. First term. Yep. Second law of Newton. This is for a single particle is Fi. I'm sorry, what did we call it? I think we called it Ri's. We said, okay, this is the force acting on a single individual particle, which is going to be equal to what? Remember, these are systems of particles. So what is this? If you go back to your notes, we say external forces, we called it F, right, plus the summation of O over J now of all the forces acting on I by all the other J particles that go from 1 to n as well. But one thing that I probably didn't tell you is, of course, I think we said this. What is Fii? Zero. That's 0, right? I think we said that. It would be nice to be able to apply a force to myself, but I unfortunately cannot do that. I always need something to touch, or if you're in space, you need thrusters. So, okay, so that's what I have there. Let me substitute it. So I don't think I need it here anymore. So this is summation over I. Well, let me do it in more than one step. Mi. Well, no, I don't need the mass anymore. This is now. This is Fi plus summation over j of Fij, and we'll leave it at that for now, minus, let's look at this one here for a second. Does this depend on the summation index? Doesn't. Does this depend on the summation index? Doesn't. So how about I do this? Summation over I bring this mi in here. I have mi ri minus mi rq cross with a, q, n. What is the summation of these guys here? Mi ri. And I'm going to continue on the other board, of course. That's a simple definition. Sorry? It's simpler than that. There's no moment there. I don't see a cross product. Remember, the moment is something definitely with a cross product. I'm just focusing on summation of, oh yeah, you're looking at the entire cross product. So I'm just looking at this piece here. Remember that AQ is really outside of the summation at this point.
Isn't that R bar times N?
Right, it's R bar, it's the definition of center of mass, position of the center of mass, right? So this is really, this summation here would give me total mass times R bar, right? Make sense? While this second, remember there is a summation in front, RQ does not depend on summation. So this, when you sum it up over I, will give you total mass of the system, RQ. So this whole second term will look like R bar minus RQ cross total mass times the acceleration of Q in N. Am I skipping too many steps, or is it clear? Summation only applies to everything that has an I, but otherwise it doesn't. So I can look at this term and say that this is equivalent to summation over I of mi times RQ. RQ is completely outside of the summation. Same for this. So that takes care of the second term. Now, here, I probably want to write just one more step. I have summation over I, and then I'm telling you that I can do this summation over j ri minus rq cross with that of fi plus fji. Do you agree with this? So I'm just doing the first term for now. So this is not equal to anything. I'm just developing the first component. Why can I move this summation here?
Because only this one has a J.
Only that one has a j. So when I fix the j and then I can sum over I, and or vice versa, I will get the same result. It's a summation. There are two summations. So if I split it in two, what I get is summation over I, summation over j, ri minus rq cross with fi plus, and of course the j that doesn't really, I can erase it from there. It doesn't make any difference. But in this case, I want to keep it just to show one thing that is important, and we actually assumed was valid the last time, but we didn't use it. So this is what I get for these fjis. And I'm telling you that this is going to be 0. Why?
It's in the direction of FJ.
Newton's third law only tells me that if there is an action, there is a reaction, equal and opposite. Doesn't tell me that they need to be on the same line of action, but I did assume that, if you recall last time, we didn't use this. We only used that the forces, internal forces, they exchange with each other are all equal and opposite. So for what we derived the last time, they do cancel each other. In this case, it's important that they share the same line of action, because when you're going to do all these cross products, and say that Ri minus Rq is a vector, that looks at this and at this, all these cross products go to 0. If this was not the case, I could not tell you that this is 0. Think about examples if you want. But again, if you don't have the strong form of the third law of Newton, you cannot do that. And of course, this doesn't even make sense that it's there because there is no summation over j. So bottom line, this is what I'm left with. Summation over I of Ri minus Rq crossed with Fi, which is, if you drop the I and the summation, is exactly what we found last time. It's the moment of the external force for a single particle, so resultant of all forces for a single particle. In this case, it's the moment of all the external forces on the system, because all these Fi's are, for each particle, Fi represents the resultant of all external forces acting on that particle, so when you sum over I, you do it for the entire system. Questions on these? Simplifications and things that go to zero? Is everything clear? So we make assumptions and then we use them. When I assume that this is true because we're doing mechanics that doesn't involve any electromagnetic forces, and so this is true, I did it because that's what I wanted to get. And that's what's valid for most mechanical systems, unless you have electromagnetic interactions. So that's the first term. And let me basically rewrite these, define this as m with respect to q. This is the summation over I of Ri minus Rq crossed with Fi. So if you have a certain number of particles, each one of them sees an external resultant force acting on it. You picked a certain point q, you have to sum all together all these cross products, all these moments of the external forces. So this is called also the real moment on the system. I believe that's the name. Doesn't really matter. It's the moment of the external forces on the system with respect to point q. And that takes care of the first term, and then the second we already said what it is. So if you allow me to just find the final expression here, this is what we have derived, that dt, the rate of change of the angular momentum with respect to generic point q in n is equal to mq, which is this vector here, minus r bar minus rq cross with ma of q in n. And I believe this also has a name. It's called the inertial moment, due to the fact that you're using a point q that may be not inertially fixed, and this is the total, it's also called apparent moment. I don't really care too much about this nomenclature here, but what I have is this equation, which, as you can see, will probably give me some differential equation because there is a rate of change here. So once I define h the way I defined it, and I take its rate of change, this is equal to the moment of all forces acting on the system, external forces, plus this additional term that takes care of the fact that the point q you have picked may be moving. Not only moving, accelerating. It can be moving, but if it doesn't have acceleration, that goes to zero. So which are the cases here where that inertial moment, that additional term is, this is important stuff here, goes to zero. So in which case d dt of h q n in n is equal to mq only. That's an easy one, right? If you pick, I'm not saying anything about q. So in many problems, it may not be the center of mass, but if rq is r bar, so your point actually becomes, so the center of mass, then you have d dt in n of h bar in n equal to m, what do we want to call this? M bar, the moment with respect to the center of mass. I think that's what I named it in my notes. I don't know. Did we give a name to that point? Just bar, right? Yep. Or
If our Q and our bar are in the same direction as the acceleration.
yes, but that may be a very special case in time. It may not be valid all times. I think the two subcases that you really want to care about are this, or option 2, Q is inertially fixed. So basically Q doesn't have acceleration. So say that it's actually corresponding to the origin of a coordinate system which is fixed to the inertial reference frame. So you, as a consequence, you get more or less the same equation. The difference is that Q doesn't need to be the center of mass. It can be also, again, a point that doesn't have an acceleration in the inertial reference frame. So for example, if you have a coordinate system fixed to the inertial reference frame, and you use the origin of that coordinate system as your point Q, that of course is an inertially fixed point, and that will give you the same result. So you don't have the second term. Those are the two cases that we really care about. When these two can be parallel, well, it could be that you have a constrained special problem when that happens, but that's, yeah. Those are the most general cases that I would envision. So this is an alternative to what we've seen last time to deal with systems of particles and find equations of motion. It's not a law, it's a derived result. It may be useful for some problems. It may be just a nightmare for other problems, so you don't want to use it. It's up to you to look at a problem and realize when it can make your life easier or not. And we're going to see an example, I guess. We're going to start an example. Any questions? What do you remember from that one problem we solved for one particle with the angular momentum? I think it was the pendulum that had the attachment point moving. What was happening when using the angular momentum instead of F equal ma? What would go away from your equations? You remember? No one remembers? I think there was some reaction force that would probably not contribute to the moment of forces, and that was going to be the nice part of doing it with angular momentum, right? So, pretty standard problem as well. This is one of those classical problems for highlighting principles here. Okay, I have two masses, A and B, equal masses, connected by a rigid massless bar here of length L. So this is L over 2, this is L over 2. Of course, center of mass is in the middle of these two. We neglect the mass of the connection. So this is also a rigid body, but it's a system of particles. Actually, this is a good question for you. Is this? We can finish this next time if we don't have time, but this is good for thinking. I told you this is a rigid body. Is it a rigid body?
Choose another point.
Right. I can have another point here that doesn't have any mass and has fixed distances from those two. You can treat that as a rigid body. The notion that rigid bodies have to have, and we'll see this probably this week, that rigid bodies have to have, they have to be in the continuum, that you need to talk about integrals at any cost is not true. A rigid body can be, well, let's generalize this, can be 3 points rigidly connected so that their mutual distances don't ever change in time. That's a rigid body. That is fine. Then also this usual potato here that we draw that is full of mass and it's continuous, and that's also a rigid body. But that's a perfectly fine one. For us, actually, rigid bodies are reference frames. So every time you can think about something that corresponds to a reference frame, that can be a rigid body. So this bar can be a reference frame. The fact that it has mass makes us able to solve the kinetics part of the problem. Otherwise, there's no kinetics, there's no forces. That doesn't make any sense. But in general, a rigid body is just a reference frame, remember. 3 points, 3 non-collinear points whose mutual distances don't change with time. That's a rigid body. If there is a mass or not, that's a different story. But okay, so I want to find the equations of motion of these. Of course. Differential equations of motion. How many do you expect? This is, of course, ground, which is inertial. Yeah, that's a good, see, that's a good thing to do. Start thinking about how many, that's the first thing you should.
So it's going to be a vertical position and horizontal position. I think going to change with time. You're going to be a couple, but there's going to be 2.
Do you think it's 2 equations of motion? Who wants to offer more or less?
Well, just one that's the body. But what he said hasn't there, because there will
So these are,
be a chance.
this is the way to think about, I think, a problem. These are two. So again, these are 2 points, 2 masses. In general, in 3D Euclidean space, which is where we're living in, 2 points need how many coordinates to be completely represented, to be able to say it's there? How many? 6. Okay, 6. Then, but then this can move along this line pretty much. I don't see how this can fly away. This can move along this line. So how many? 2. I'm down to 2 already. And this is a planar problem, of course. I'm assuming that they don't come out this way. You're going to the board. So that's already 2. Plus, this,
Related one to the other by the-
they are connected. So this is really just one equation of motion that I should see. And in fact, I think the problem, the way it's this is probably on your book. I don't remember. I think it's they actually give you this variable here. And again, if the drawing is already giving you some stuff, there must be a reason. So I think really my differential equation, if we end up choosing the theta angle that is given to us, maybe just 1. But that's a good way of thinking. You want to know how many equations you should have in the end. Otherwise, you're going nowhere. Okay, so what do? The usual stuff here. We choose reference frames, right? And that's the other question. How many? You say 2? I guess G is the ground. And let's say that for this one we have origin at O. Say EX is along OA. Why not? EY is along OB. And EZ is, what is EZ? EX cross with EY. So that's what I have. EX this way, EY against the gravity vector, and EZ is coming out of the page, right? For example. Which is the other one you want to use?
The line that connects the 2 nails, AB.
So call this arm. I mean, I think we always used A. We call this the arm. So we say the other reference frame is A, the arm. And that is, okay, what do you want to use as origin?
C is the center point.
As long as it's fixed in that reference frame, it's A and B would be fine as well, right? And then I guess little ex along CA. You like that? And then you thought about 2 because there is a rotation, right? It's obviously there is one rotation here that's happening. So I guess we want to use the axis of rotation, which is EZ. So B little EZ equal to B EZ. And little EY is going to be equal to EZ cross with EX. Okay, so on this sketch here, I have the two EZs, they're the same, and then I have little EZ that it's going down this way, right? I'm sorry, little EX going down this way. This angle is theta. Correct? Not correct? It looks okay to me. Origin. Okay, good. So we have the reference frames and the coordinate systems. Good. Now, if I want to use, as I'm sure you have imagined, the angular momentum here, let's just take the time to write down definitions. I think, again, this class doesn't have much in terms of memorizing things, and you can use your book. But it's good to start from the definitions of the tools that you're going to use. Well, in this case, n is g, right? So I want h in g with respect to which point? You want to do C? You can do C. You can do whatever you want. I mean, it's up to you. You can do O. That's an inertially fixed point. That's the other case where the second term goes away, right?
But C happens to be
Center of mass.
R-bar.
Yeah. In this case, it is. OK, so we're going to do it with C. Let's do it with C. And then I'll tell you there's probably a better point that you can pick. But let's see what we get with C.
And in this case, C is R-bar because the masses are equal, right? Because they both have the same mass.
Yes, but remember that at some point you're going to write the following: m with respect to C, right? Or, well, C is basically h bar, right? So m bar, and so this is going a little bit ahead of myself, but this is, unfortunately, when you do it with angular momentum, this is something you need to do before you start writing anything, before you do kinematics, etc., because you have to pick that point. So you really have to do it ahead of time. So here I'm going to have the summation, well, in this case, I goes from 1 to 2, right, of what? Well, actually, yeah, it's Ri, let me write it, minus R bar, right? Cross with Fi, which in this case happens to be what? Well, Ri is Ra, Rb, right? I have two of them. And here I have to deal with the forces that act on A and B. And so I have one by one. Let's do particle A. Ra minus, I know it seems like I'm jumping into calculations already. I'm not. I'm just thinking about the point that I'm picking here, if it's really going to make my life easier. Minus R bar. These are all symbolic calculations, just to see if I'm doing something that will help me. So all the forces that act on A, if you look at A, you have what? mg. There is no friction. I didn't tell you that, but if I don't tell you there is friction, there is no friction. And then there is the reaction in A, right? And so this is going to be equal to mg plus na. And you'll have to deal with that. Plus Rb, oops, minus, same, R bar. And of course, these vectors, they make sense, right? Ra minus Rb, it's the vector that connects the two. We can compute it later. And this is crossed with, let's see, mg, same, plus n in B, where the body diagram here looks a little different for, that's that B. So this was point A, this is point B. I have mg that goes down the same way, doesn't change because the same mass. But then I have these other force here, nb, that I don't know. So even before I start computing what h is, with respect to the center of mass, and then I take its rate of change, and then I equate that to this monster here. You think there's something better we can pick? Of course there is. I mean, I'm telling you that there is, but what was the beauty of that problem with the pendulum when we picked the attachment point? That the reaction forces would not contribute to the moment, right, of the forces. Is there a point where these two, yeah, we'll finish it next time, but is there a point where these two really will not show? That's the exercise that you have to do before you dig into deciding even where the point is. Because here I don't see that they go away. I mean, this is RA minus R bar is what? Is this vector here, right? And I don't see that cross product really, because those two forces are in this direction, doesn't really go to zero. There's nothing that really simplifies. The same for the other point up here. Oh, it's even worse. I mean, it's not worse. It's the angle is actually 90 degrees now. So it doesn't really. What cancels? Nothing cancels if I pick O. Oh, that one. It cancels the gravity one. That's it.
You can pick a point at there.
Right. So Q is any point, right? So the fact that the formula we found has the second term that goes to zero, which is very attractive, doesn't mean that you have to put yourself in that situation, because it may actually be more complicated. If I pick this point up here, which is not inertially fixed, it's not even part of the rigid body, it's moving all over the place, they all go to zero. Because gravity, reaction, well, this doesn't. Gravity, but who cares? That's nice. Reaction. The reactions go away. They're pointing at Q. So the cross product will go to zero. So don't rush into using that equation in the form that looks like it's shorter, because it may actually be longer. So we can try to do it this way. I'm not 100% sure that we'll be able to get rid of these reaction forces. So let's start writing some vectors here by picking. So do we want to do with C? I think we should do with C, and then next time we'll do with Q, because it will be simpler. But let's start writing this, and again we'll finish it next time. So what is H bar? What is the definition? In general, start from the definition: Ri minus R bar cross with M V I in G minus V bar in G. Correct? That's the definition? So let's forget about this for a second. We'll come back to this next time. Okay, so in this particular case, we have two particles. Let's spell this out. That's, again, RA minus R bar cross with M V A G minus V bar G plus RB, sorry, RB minus R bar cross with M VA ground minus V of the center of mass with respect to the ground. So now I can start using my coordinate systems here. And one observation I'm making is RA is what? I have, that thing is L, so L sine of theta EX. And RB, it's L cosine of theta EY. I'm starting to think that probably I don't actually need the second reference frame and coordinate system, which is probably actually what is going to happen here. But as I made the comment last time or a couple of lectures ago, it's better to have more reference frames than missing a reference frame and having huge expressions that that make your life miserable. So if you have started the problem and you have set up reference frames and coordinate systems and you realize along solving the problem that you didn't need them, you don't need to go back to the first page and burn it. It's fine, leave it there. No one is going to punish you for picking that. Actually, I think if in a year from now I completely forget this problem, I will probably do the same. I will set up 2 of them because I see a rotation. All right, so we should finish it next time. We don't have enough time but you can continue by yourself. I encourage you to do that. And so we'll finish it this way probably, and definitely want to see with point Q.